Alrighty then. Yes, yes, gotta let the hair down and everything. All right, my monastery life, episode number 2. Why? Because we can. Bosons are back on the tables. Why? Because I put it into the description, so we shall make it so I claim. Yes, it's okay. We're wireless. Don't mind me. It's not like I just threw a hot cup of coffee and I need to be a complete savage and cool it down with water rather than cream. Why? Because I am a terrible human being and I need my caffeine. So, what are we going to talk about today? All right. So, we did a little bit of the backstory and everything, and we'll give time. We'll let folks come in. I'll bloviate for a few minutes, and then we can get right into it, my friends. All right. So, we're wrapping up the story. How the heck I got here? Long story short, just by happenstance, via the power of the internet, I came across some things. The other me on G2 results. It's like, all right, nobody knows what's going on. I just happened by clicking a link on the internet, came across somebody that at least, at least before it was publicly announced, it had a prediction. Now it's gone through a bunch of changes as we get more data and everything. Um, but then at least the updated released ones with the second edition of 44, it even with the reduced error bars, it was still there. Now you can say maybe that was just a stroke of luck. Maybe it was. Maybe there is something to this method. Uh, Ironically, unironically, it actually happens to be based upon the figure eight knot. Why? What is that? Oh God! I'm going to try to draw this. I tried those, and I'm going to butcher this. Okay, it's like the trefoil with an additional loop. So what's the easiest? Okay, I don't want to screw this up, so let's actually do this. Hey, Rick, thank you for joining, my friend. We'll see which territory we get into. So, hyper. Oh, wow, I can't even spell. Here we go. Hyper. Okay, just so I. Oh, wow, you didn't even autocomplete. Wow. Failure. All right. All right. So it's got the loop, the loop. Let's go into one of the easier forms. Okay. So it's normally something like this. It's like, all right, we got our go. This goes here. This guy goes here. Uh, that's terrible. I should have probably actually thought about this before I started to do it. It's okay. It's okay. The beautiful part about live internet. You never know what's going to happen. All right. This guy goes down, crosses, and then we have this guy goes there. And oh, hey, buddy. Are you helping? Oh, are you a helper? Yeah. Oh, look. Is it helpy Tubbsy? Yeah. You want to help me draw? It's all right. I swear it's not a panther. Oh, okay. Try to do less murder outside. So Kyle Hill did a video for Halloween. It's like why you should never let your cats outside. I watched 1 minute of it and I stopped watching it. And I can't just help feel he might be right. Some cats just like going out and destroying everything they can. That's aside from the point. Okay. So wow. How bad did I draw this? No, 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 no. Well, this guy goes over there. That guy goes under. All right, so you go under. Uh, that's lying. Oh, you need attention? Is somebody not paying attention to you? Is that the problem? Oh, that goes over. That goes under. Uh, and then you. All right. So, aside from embarrassing myself, let's actually do the one that I actually know how to draw. Okay, this guy. I'm sorry, just in my head, I am not good at doing that. All right. So we just have this loop, and then that goes over there. This guy. Wow. You'd think I have never actually sat down and drawn these more than once. All right, let me fail at this a little bit more. All right, so we got that guy. All right, that guy goes all the way. All right, down there. Ah, and then uh, yeah. Ah, okay. There we go. All right. And that guy is all the way around to here. All right. Oh, and this guy. All right. So he goes there. They go there. You go there. And is that it? It looks mostly like it. Yeah. All right. I think it's something like that. All right. The whole point of that tangent was that, all right, if something is based upon a knot, as you tighten it up, it should actually get better. That was the whole point about me drawing this thing that I probably was actually standing in front of the whole time. It's okay. It's gone now. What do we got? Yes, something to sneeze at, Rick. There's a lot of interesting things. All right. So I'm just going to get into bosons because that's kind of my current little thing and my at least current project that I need to at least finish before I go back to the East Coast is to write a couple of short papers, submit them to the powers that be. We'll see. Before I'm going to complain about stuff, I need to go through the process. So then I can complain about it later. Uh, who knows? Who knows? And I just figured it's like, all right, I finally installed LaTeX and everything like that. LaTeX, latex, I don't know. It depends on how you have it. Apparently, it's text based. And when you actually install it, it's a tiny little thing, and then you're just lining things up. I'm like, all right, it seems like a stripped down, like word pad just with a lining thing. I'm sure it works, and I'm sure there's plenty of reasons people love it. It makes pretty things. And you can also Wolfram's supposed to be able to output things in LaTeX style format or textile format, however they have it there. And I'm gonna just do a couple of things because I know it can be hard, especially like if you're like, all right, I have a great idea. It's like we need to frame this whole thing. Now, you can do that. It's extremely difficult, especially if you're differing from a lot of the current zeitgeist, so to speak. All right. So, what am I actually talking about here? Okay. So basically, I'm going to attempt to put together a couple of short papers. I still get recommended fads like quantum space time, whatever that 400-page thing that's on academia like every 3, 4 weeks or something, as well as asking me, did you write this? Did you write this? No, I did not write those things. I'm sure recommending them would never incentivize somebody to do the wrong thing. Sure, I wrote all these hundreds of papers that have no claim person. I don't know about that stuff, but we're going to be talking about is bosons. And one of the reasons why I want to do this is because by actually speaking, by actually going through answering some questions and everything, we can actually try to get a better feel for what's going on and try to make myself more coherent so that when I put things to paper, so to speak, I think this might be the actual last generation where that will make any sense. Because that's been a long-standing thing. We're talking about it last night. It's like putting pen to paper. It's like, and that's not what I'm actually doing. I'm actually like typing it up in programs and everything. But you think about it, it's like, all right, like 50 years ago, you can put a pen to paper, maybe a typewriter or something. For hundreds of years, you put pen to paper, quill to parchment. And now we're not going to be able to say that anymore. I'm sure there's a lot of trees that are very happy for that. Hey, I like oxygen as much as the next person on Earth. But what we're going to try to do is take things that don't seem to be within the conversation, at least from what I've seen, aren't on the archive, or at least other places that I really see things. It's like, all right, let's put some stuff out there. Because I have heard, at least according to the smellologist that Anastasia and Shiloh had on, I know that's not his name. But he was like the perfume dude, and he kind of came at it like a science, like an extremely good scientist is like, hey, listen, this is what the evidence seems to be. Is that what it is? I don't know. We're going to need more evidence and everything. That's the scientific method that I like. Just because it's like, all right, could be wrong, but if the evidence kind of starts keeping on going in a particular direction, that could probably give you some confidence. Okay. What the heck's that have to do with boson? Okay. One last side tangent before we get to this. So, like we were talking about yesterday, let me get a better pen. Excuse me, marker, because that's how we mark things with markers. This good dude. All right, let's messily wipe that over. Okay. So a lot of this comes from looking at ways to reduce or simplify things. Within the Wolfram school of thought, some may say we're looking for computational reducibility. Okay. Why do I say this? Because when we've got some terms, like let's just say alpha here, aka the fine structure constant, and that is currently defined as elementary charge. So the electric charge associated with a proton or an electron, and since it's squared, it's going to be a positive answer, even if it's negative charge. All right, so we have elementary charge. That's all over 4 I H bar elementary action times C, the speed of light, times E naught, aka the electric constant. All right, that's how we get basically the inverse of about 1 over 137-ish, or like 137.035999. And some people disagree. Well, I happen to have some disagreement there. I'm biased, though. All right. So you look at this thing, you're like, it's freaking crazy. But it's all right. So we got something, some electric charge, square charge divided by like maybe a sphere, by the elementary unit of action, by the speed of light, and by the electric constant. It's like, I don't know about you guys, but for me parsing that, it's like my brain, it feels like smoke's coming out of my ears. And it's not just from overcharged AirPods. However, when you look at it, it's like, wait a second. What is this whole term here? Well, you put it into Wolfram Alpha, you get something, and it doesn't return a dimension because you're like, it doesn't make any sense. It's like, okay. So if you take the square root of it, you got a very familiar friend. Q sub P. Oh, I should actually make that more of a sub. All right, Q sub P. No, yes, Q sub P, aka the Planck charge. Like, wait a second, that whole thing's square rooted. Could we simplify this in a way that makes sense and saves me like keystrokes on the keyboard? Again, part of it is laziness. And then one realizes that whole expression is the equivalent to elementary charge over the Planck charge, and you square the whole thing. So we go to two terms rather than one, depending on how you want to count pi, 1, 2, 3, 4, 5. Seems to be a little bit simpler. So what are we doing? I don't know. It seems to be partitioning the maximal charge, I claim, by the elementary basis of charge, maybe squared. So at least that's a little bit more intuitive for me. Like we got some more folks rolling in. Hey, what's going on, Mark? Mark, it's just stuff doing things. Now, the particular stuff and the particular things it's doing may vary. Uh, oh, okay, yeah. Okay, hey, any way we can easily get transformations from one document style to the other. All I know is, hey, I just remember back in the day, you open something in a file, you try to open in another file. Maybe it doesn't quite match. And we go through all these issues while trying to translate it. It's good to know that some things never change. little sarcasm there for you. Pardon. Apologies. All right. So, what is the point? Why am I showing all this stuff? People already know this. This is nothing new. Okay. So, it's nothing new because at one point I heard people talking about like the electroweak force, the big boson and everything. And it's like, well, I don't think we spent much time thinking about that. So I'm like, can I maybe intuit something? And then it's like, all right. So you do something like, what is it? Okay, so we'll just do H for Higgs. So, no, sorry. Gotta stick to the real notation. Mass sub H is the mass of the Higgs. I don't know. How about something that we treat as a unit one? Divided by the Planck mass. M sub P. And you look at this and you're like, oh, this is about, is it 10 to like the negative 17, maybe 16, 9.8 times 60. So it's about 17 orders of magnitudes difference. And even, what is it? I think it's Sierra Marletto. I'm trying to remember your name, but she's the physicist that was working experimentally that Sean Carroll had on. They were talking about like the weak force and the Higgs and the mystery. And it's like, why are there like 17 orders of magnitude? But she's like, well, it should actually be squared. All right. So if you square this, you end up at about negative 34 orders of magnitude. Okay. Now, if you're a crazy person like myself, and you spend far too much time on the internet and Wolfram Alpha, you start to notice some of the things that pop out. And one of the things that I noticed with a construction like this, 10 to the minus 34. Okay, it's that in alone, okay, whatever. We have no idea why. When you go into Wolfram Alpha and you do something like this, you get approximately about 1.05 times 10 to the negative 34. Now, when you look at that, and maybe you spent past year or so like staring at data points and becoming familiar with different trends that are built into the constants of nature, you realize, wait a second, this happens to be the first couple of digits and the order of magnitude of H bar. WTF, mate? It's like, wait a second. Now, to be fair, is this something special to notice? No. If you happen to spend time on it and you happen to have gone through where we actually have the more up to date measurements now, yeah, because was it the Higgs was between originally was like 114 to 160 giga electron volts. It's kind of a large range. It's like a couple handfuls of protons. Okay, when I say handfuls of protons, I should probably specify a couple of dozen. Couple handfuls of protons is probably okay. We want to be accurate here. Okay. So you notice that and you're like, that's interesting. It's like, but it's only three significant digits. And then you realize the most up to date measurements of the Higgs, you only really have about three digits, significant digits of confidence. We think it's about 125 GeV, probably on the lower half there. We've had measurements more recently, about 124 and a half, and then about 126-ish or so. So it's like, all right, we believe it's about 125 GeV for its mass energy equivalent, aka E equals mc squared, blah, blah, blah. We express it in electron volts because we can. And then that's technically how we're actually measuring it. Okay. So I'm like, wait a second. We have like three digits. I'm like, let me entertain a crazy idea. What if there were something to this? What if I learn from that? It's like you get an interesting answer. I'm like, what if I assume this expression was correct? What would I need to modify it by for it to be precisely H bar? Now, one might not have any idea how to go about that. Basically, you just kind of do some basic algebra. And the reason why I say that is because if we only know the mass of the Higgs to like three significant digits, but we know the Planck mass to at least five, seven with our error bars, and we back in 2019 defined H bar to 10 significant digits. We had 12 because I remember going through and Thad had originally in the first copy, like 44, he had 12 significant digits. And there were kind of large error bars for the last two. So they lopped it off at 10 significant digits. This is how we define the elementary unit of action, H bar. Okay. So all really one really has to do is you can do this construction, you can divide it by that, and you just set it equal to one. Now, you would have to set it equal to 1 joule second or an iterative. So basically, the way I do it for just aesthetics is I flip it upside down, as Rick, who's in the chat, as well as Thad and John believes, has stressed to me. So I just take m sub p, the Planck mass, and you divide it by m sub h, the Higgs mass, and again, we square this whole dang thing. We throw in h bar, and then we set it equal to, since it does have units, as somebody on one of the discords pointed out to me as I was trying to do the absolute value, and they didn't like that notation, and I'm sure nobody argues for argument's sake on the internet. 1 joule second, because h bar elementary unit of action is expressed in joule seconds, aka energy mass area rate, because it's a mass term, it's a length square term divided by a time term. Seconds. God, I can't spell seconds. Terrible. All right. So if you set it up like this, all you really got to do is, well, we have confidence in this to 5 digits and confidence in this to 10 digits. What if you did a crazy thing and you, I don't know, solve for X kilograms? Because that's a mass term. That's a mass term. You divide a mass term by a mass term. It cancels out. It's squared. So it's a dimensionless number. You're multiplying it by a dimension-full number and setting it equal to 1. So if you solve for that, I'm not going to, I remember it in GeV because it's easier. So this leads to x times c squared, blah, 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 equals 125.37 GeV. Now, I would love to call this a prediction. I can't. I can't call it a prediction. Why? Well, to be fair, we've already measured the Higgs boson at that mass energy value. I'm pretty sure this was it. I think one of the runs, it was either 137, 138. And then before the more recent measurement, this is within about 3 sigma of its current world average. They have it about 125.11 GeV. Wolfram Alpha lists like 125.18 GeV. Like 2 years ago, I think it was like 125.35 GeV. So it's basically just right where a lot of people have claimed it to be. Now, again, this, like many things, is probably wrong. I'm sure there's some geometric action. I mean, how could it just be like, all right, well, let's just take this. Let's just recognize the first couple of digits and put this in. Again, I spent a lot of time going down Wolfram holes. Now, maybe there is nothing to this at all. Let me catch up with some of our friends in the chat as well. Oh, cool. Oh, that would be awesome. Yeah, dude, Rick, if you could send that to me, that would be actually awesome. Anything to make LaTeX easier. Okay. No. All right. Am I still frozen? I don't think I'm frozen anymore. I seem to be moving. It says we're live. I'm at least trusting the technology this far. Okay. So maybe maybe there's just nothing to that at all. Now, the other interesting thing that one finds is that, okay, we don't square this. What happens if we put in this number for the mass of the Higgs? So, okay, we go over here, What happens if we just do m sub h, so the mass of the Higgs, divide by the Planck mass, m sub p. Again, this is a dimensionless number. It comes out with a value. So if we plug in those numbers right here, we'll just do the standard Wolfram alpha here. We'll just bring it up and show everybody. Boom. And share screen. Tab. This guy. All right. So let's do this. So Higgs mass. Be close enough to get a good estimate. Divided by the Planck mass. Okay. Okay, so you get about 10 to the negative 17. Okay. So we went over that before. You get like 10 to the negative 17. Now, okay, I need to swap this around. There's a reason. All right. I inversed myself out. I'm only off by 34 orders of magnitude for what I'm looking for. Derp. All right. So if we just do that instead, yeah. So I did that. Okay. No, that was correct. I rewrote it that way. All right. So when you do blank mass divided by the Higgs mass, okay. Let's swap this guy around. That off, put you there. Okay, that looks a little bit better. Okay, it's a little different again. There's some rounding there, but it gives you approximately 9.8 times 10 to the 16th power. Wow, that's a pretty big number right there. Oh, let me stop screen. Okay. All right, so we've got this number over here. 9.8 times 10 to the 16. Huh. I mean, again, it's a dimensionless number. But apparently nowadays you start hearing about, well, there's like some dimensional mixing that goes on at a particular points. Like dimensional mixing? That sounds like alchemy to me. Hey, we don't use that term. We use the term advanced transformational chemistry. Just kind of like the ether. We don't say that word. It's totally not the ether. You can say superfluid. You can say the fabric of reality. You can say space time, but no ether. Why? I don't know. I read a book, something like there was no elephants before. So they end up having an elephant in the end. Go figure. But getting back to potential reality, okay, 9.8 times 10 to the 16. Is there anything interesting that happens in any other dimensional format around that point? Now, I'm probably off here. When does electroweak uh, when does the electroweak force kind of break from the other forces, or at least as we understand it? I think it's around 10 to the 16, 10 to the 17 Kelvin, something like that. I'm just saying it's a very interesting relationship, and then even like the Higgs and Compton wavelengths and everything. It's, oh, where's it come out? Oh, at the electroweak scale. It's, oh, imagine my shock. It's okay though. It's not charged. That's the W bosons. But let's see. Oh yeah, well that's the thing. Most things are wrong. Most things we do are wrong. We're seeking to be less wrong. We want to be as correct as we can. We realize that, well, we're inherently error bound. We're going to have errors. So that's why I believe science is the quest to be less wrong. Uh, so, okay, so Grant, the interesting thing with this is there are a lot of ways to compare things, and I'm pretty sure there are a number of other ways you can compare different mass elements within the constants of nature. I mean, we do even have that on the poster as well. The claim for this is if you're using Planck units, aka maybe we'll call it natural units. If we're using natural units, a lot of times you can just set them equal to one. So it's somebody on Discord, they found like some interesting relationship that I haven't seen before about the mass energy of a black hole, and then you basically take the Hawking temperature of that black hole and you throw it into the Landauer limit and everything, and then it seems to hold the relation that it always ends up being 1/log 4. It's It was very interesting. I was kind of proud of myself. I was going through a little notebook doing the dimensional analysis. I had to use Wolfram Alpha just at least once to double check myself. But it's like, all right, this appears to be Y. It's like, really? Something's 4. I don't know. It's not like you have like a 4 square orthogonality, this, that. I don't know. It was an interesting relationship. And at one point, Thad the other day, he's like, I love algebra. And it's like, I didn't say it. I have been thinking the same thing because I'm like, oh my God, there's a reason for doing it rather than it's like if Sally has 4 apples and then Timmy has 5 apples, I'll respect to Timmy and Sally. I don't care how many apples they have as long as the kids aren't hungry. Now, if you say, oh my God, you could do little things like this, if there was something to this, again, maybe there's just all some numerology, maybe there's nothing to this, but let me at least provide a little mimetic evidence. So basically, the long story short is if we're using Planck units, we can express those values as one, which makes the math a heck of a lot easier. And you can find some interesting relationships that we won't go into all of them. Some of them should probably be kept quiet for now out of respect to certain people that had helped us come there. But where are we right? Oh yes, physics temperature. Let's see. Uh, was it phase breaking symmetry? Where was that? Uh, I think universe temperature. Something like I think it was this guy. All right, let's bring this guy up. All right. Now again, take this for what it's worth. This was posted on the Physics Stack Exchange. All right. So what we got here? All right. So AKA 10 to the 32 is the Planck temperature, AKA the maximum temperature within our realm of persistence, so to speak. All right. And as you're going down, 10 to the 28, what are those? Kelvin, temperature in Kelvin. All right. So what is this? We have about 10 to the 17 behind us. That's probably around here. We go across. Okay, so we seem to be within about a magnitude of the electroweak transition there. Now, again, I'm not saying this is exactly how it is, and again, this is you can see the time we're going from. All right, so about 1 Planck seconds, or excuse me, 1 second. Yeah, one second basically is about there. So we're at 1 second there, and now we're at 10 to the 7 years, now 10 to the 10. So that's where we're getting our 13.8 billion year estimated age of where we live here is yeah, that scale goes from really small numbers to really big numbers. But hey, I don't know. We go across, I'm going up, I'm going up. Okay, so it's probably less than that, about 10. I don't know. It seems to be within a magnitude. Is that additional evidence if we put that in Kelvin, the relationship? I mean, okay, hold on. Let me embiggen this over here. All right. So basically, the whole claim would be if you're going to take this all in a nutshell, it's like, why does the Higgs have the mass that the Higgs does? The answer to that, I claim, would be the Higgs has the mass that the Higgs does, so that the elementary unit of action, h bar, can do its thing. And if we don't necessarily have the best concept for things happening, basically, if we need to cool down so much for stuff to start doing the different things itself, I mean, that makes sense to me. Now, I'm not saying that that's what it is. I understand. I just claim that's what it is. But again, I'm trying to support my argument with different evidence. If the evidence leads in a different direction, if somebody has a better idea, something that's like, oh my God, duh, I am happy to go with that. But as of right now, this is the current paper that I am working on, couple of pages. I don't even know if I'll include the temperature thing just because that might be off by a magnitude or so. But at least this simple thing that seems to get at least the first three digits right, that it's kind of already been measured at this magnitude. Again, not a prediction. It's more like if these measurements end up holding out and we get some more significant digits, and we could say, all right, it looks like it's 125.3 or 37, because the initial, I think the Large Hadron Collider, I think first measurements, or at least that I found on the archive of it, it was like 125.3, and then they had the statistical and experimental error in there, and that was about a gig electron volt in there, maybe a little less. So again, it would be a fantastic explanation. I need to study more about the early the early universe, so to speak, about the temperature, get some more information, see if I could relate it. And hey, maybe it's not related at all, but it does seem to beggar the question. I'm like, all right, well, if this is about the magnitude where you got the electroweak force kind of like breaking, if you would, away, because now we're cool enough so that we can start taking actions. So all of our dimensional ingredients of the stuff, so to speak, can start doing the things that we know about in the world in which we live. Now, I realize that jumped all over the place, but it's okay. It's okay. We're learning together. Blah, 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 blah. Nine grants in three. Applications of 19. What is this? Applications of 19 by 10 to 16. This ratio is also accurate. Good students. Scenario. High energy customers. Um. Oh, okay. Okay. Yeah, I see. That's supposed to be a 9 times 10 to the 16. I got you. So he plays six above 410. Like mashes with a small and approximately emits this. Now, I'm trying to. Sorry. Hold on, let me put it down. Because I was going to say, I'm like, wait a second. I have at least checked some of these things a couple of times. I'm sorry. Hold on, let me. Well, that didn't help, did it? Oh, just broke something. Hold on, let's do this. Let's get a little. Oh God! Wow. Where is that coming from? Oh, probably the extra lights. But I don't need them. See, is that better? Nope. It turned off everything except the actual thing. All right, let's just do this and go mobile. All right. It doesn't even. All right. So this is what we have here. So grant we have. Uh, hold on. Let me actually show it out again. It's just easier. I'm not good at balancing the stuff. Which I tried that yesterday, and I realized for a question like this, it's much easier to actually go into it. So I'll just go. All right. I'll just go into this guy. Boom. Okay. So that's as far as like any type of temperature thing. And again, that's an assumption. There are no dimensions attached to that. That's a dimensionless ratio. That's the Planck mass divided by the Higgs mass. Again, um, about the first three digits I claim would be correct. After that, basically we have at least what seems like a reasonable way to take an educated guess at it. I think it's already been measured at that level. But the claim here is how we're getting to that is we square the whole thing. And you get basically this value here. Now, when you take that value there, that's dimensionless, you multiply it by h bar, the elementary unit of action. Okay. This is what caught my ire, if you would. When I did that, I'm like, Listen, that's about 1 joule second, aka 10 to the 7 erg seconds. I believe the erg is a highly underutilized value that's been depreciated before its time. It's anytime I see 10 to the 7 or 10 to the -7, that makes me a little giddy because that is part of the model that we're postulating. And I know some other folks have found other interesting things at around that magnitude there. So my whole scientific method was essentially that, well, what if it was one? How could I figure that out? All right, you just take that whole thing. So you take this term, the Higgs mass, solve for x, and that's a kilogram term that was in there. So we're putting in kilograms. H bar is a joule second term, so we add 1 joule second. And when we hit enter, and then all the knowledge and mathematics and everything basically gets done by the Wolfram language for us here. You get this value, which very interestingly, since it's a squared term, it gives us both a positive and a negative answer. How do you have negative mass? It's a fantastic question. That's why it's a beautiful thing when you can actually start to parse things and then have it reveal more structure, if you would. So that's a kilogram term. So since we solve for kilograms, we hold, oh my God, I'm sorry. I forgot. Let me actually click on the thing. I'm so used to opening up new tabs. That's why I have so many dang tabs open. 10 to the -25, that's a kilogram unit. Let's find the energy equivalent, C squared. Okay, what do we get? Wait a second. 125.37 gigaelectron volts. That was what I wrote on the board. Because I had done this and done a video and then promoted it out because it seemed like a very useful thing that I think could be useful. And again, it's really exciting because apparently they're getting, speaking of colliders here, initial beam operation. Apparently, one of the big things with the problem with the hadron colliders is you're basically colliding protons typically together. And there's a whole bunch of stuff that seems to be coming out and everything. Whereas if you're just colliding electrons or muons together, muons are essentially, they're referred to as the heavier cousins, 206 times approximately more heavy than an electron. Because an electron's like 10 to the -31 kilograms. Itty bitty. A proton is like 10 to the negative, what's it, 27 kilograms. It's itty bitty too, but a great bit bittier than an electron. Okay. A muon getting into the magnitude of a proton, but as far as we know, it's an elementary particle. So if you smash two muons together, you don't have to worry about all the other stuff coming. Apparently, the big thing with that is one, you need to make the muons. What do? You basically, what is that? It's like firing gamma rays or something like that, or electrons into like lead. And you collect the muons. And the only problem with a muon is it's kind of unstable and it decays after, what is it? Like milliseconds, like 2.5 milliseconds, microseconds, ridiculously short period of time. But if you can accelerate it, you can kind of get a little bit more juice out of it. Apparently, when you're creating them, you're kind of, I think, I think it was Kier Malego. I'm sorry, I'm butchering your name, but she was saying that you kind of get like a poofy cloud, and apparently you need to get that poofy cloud to align and get them in order, so you're actually like getting muons in line. So it's, I guess it's like herding cats or something. It's supposed to be very difficult. Apparently they were able to do it recently. I saw that, so it's like, oh, sounds like we're one step closer to a muon collider. Again, I'm very biased. Why? Well, I'd love to see if, I don't know, maybe some of these numbers actually bore out, and if we're wrong and it ends up being a different number, it's like, all right, well, at least we're in the ballpark. Maybe there's this very particular geometric action, perhaps a small geometric action. Now, I'm totally not saying that it's the Geeskind manifold, which also happens to be the volume of a hyperbolic tetrahedra. Don't worry about those words for those just tuning in. That's a lot of the deep lore. There's some more stuff on the channel, and feel free to uh, comment along the way. Let me see. Okay. I agree, Rick. Planck mass is a maximal, not a minimal. So then see, that's the interesting thing, because even was it at one point we had a discussion with John Williamson and Arnie from the Quisical Society. God rest John's soul. But we'd kind of gone through, and Thad had brought that up. He's like, oh, I happen to believe the Planck mass is the maximal one. And he's like, it was an interesting thing, because I mean, John Williamson, he had worked his life as a physicist, and he's like, that day, he's like, I actually hadn't thought of it that way. But it is an interesting thing. And if you have some folks out there, and even they had created the Quantum Bicycle Society, to help have a bit more some heterodox, having some different folks come in, and maybe the ideas are wrong, but I still need to reach out to Dr. Vivian Robinson. Um, he had some model. It's like, all right, what if the nuclear force, or what if the strong force was another expression, the electromagnetism? And you're like, oh, well, that's crazy. And then you kind of see it. It's like, all right, what happens if we had those overlapping force lines, and it kind of cinches it together? I'm like, you had some pretty pictures. I didn't sit down and go through all the calculations and everything. And even John at the time when they were looking at the presentation was like, that's a very interesting claim. And you know what? I would love it to be right, because then it would simplify things. And it's like you have another way to unify other observed forces that we see. So, yeah. Blah, blah, blah. Is the power to okay? Yeah. That's right. It's yeah. I'm sorry. It's the little thing over there. I think it's popping in from a little bit of the side. Oh, let me see. It's this. Uh, yeah, there's still a power too. Yeah, that's why I have the side screen and everything, so I can jump into it as well. Yeah. Ah, there we go. 2.2 microseconds. That sounds right. Uh, see, I would love to see the muon collider, because it's like at that point we should be able to create lots of Higgs bosons. Again, I'm not saying that's a good thing or a bad thing, but we should be able to, knowing the stuff that's going on, it should be a lot easier to compute with higher accuracy, more significant digits, because that's what we're looking for. Because right now, if we have like three significant digits, so okay. That is very, yeah, that thing that's blocked out by the light right there. Let me back. Okay. So yeah, that thing on top is actually, uh, this is basically just elementary charge. So the whole thing was, the concept for this just came from just noticing that if you take the fine structure constant, or alpha, it's defined by elementary charge squared all over 4 pi h bar c e naught. It's like, well, that's a whole mouthful. And then you realize, wait a second. When you reduce this all down, you just write it as elementary charge over Planck charge, square the whole dang thing, and it's equivalent. Because that's what this whole expression breaks down into, is the Planck charge squared. So I'm like, all right, you write it like this. So I'm like, all right, that seems to be a powerful, simple, I would claim beautiful expression. So I just extended it to this, played it around as Rick and some other folks have conditioned me to look at. That, oh, let's look at this, and then you got this number, like, oh, that's like the first three digits of h bar at the correct magnitude. Or if I swap this upside down, and rather than having to divide by h bar, is multiply by h bar, solve for x, what we would claim, our claim that the Higgs mass, if this was equal to precisely 1 joule second. And again, it's a claim. We're going to need to follow the evidence. And of course, the evidence could show we're wrong. It probably will. If it doesn't, that would be interesting. Now, it might not be as interesting as if it was wrong. If it's wrong, then you'd have to have another geometric action in there. But it's like, all right, hypothetically, let's put on maximum speculation. All right. Let's start with at the point with at least current standard model as far as we know it. All right. Let's assume maybe we had a primordial atom. Maybe everything was crunched together at the Planck density. What's the Planck density? It's like 10 to the 96 kilograms per cubic meter. Why is that number? I may have some reasons, but we're gonna have to save that for another episode. Um, but let's just say, boom, kablooey, whatever. Stuff and things start expanding out. Matter is being made. And, all right, quark gluon planet, very hot, very hot. Maybe after, I don't know, like half a second or so, let's just say at about, I don't know, around 10 to the 17 degrees, things cooled off enough that the Higgs kind of gets crystallized in a particular energy. Things keep on doing their thing. And basically, as soon as the Higgs takes its value at approximately 125 GeV and you get below 9.8 times 10 to the 16 Kelvin, H bar, the elementary unit of its action, can start doing its thing. So now we have our dimensional ingredients. H bar is mass, area, rate. So what is that? That's just mass times a length term squared. So it's an area divided by a unit of time. All right, so that's how we get action. So what if in order for action as we know it to start doing its thing, we need to cool down to the point where the Higgs ends up being, I don't know, some people use the term crystallized in the whole thing. I still need to learn this. This is just a very basic calculation that I just look at the data, do some crunching, and I still need to learn a lot more behind it because, okay, maybe just a lucky guess. If it's a lucky guess, that's fantastic. That doesn't really tell us anything. I mean, okay, maybe it gives some intuition, but that's what I'm trying to figure out. And that's why I'm doing these things because there's a lot of smart people. I have met a lot more geniuses than like technically geniuses, according to whatever common parlance, than than you might expect. Because statistics is a thing. If you talk to enough people on the internet, and you can survive enough of those conversations without completely losing one's mind, arguably here, um, you can learn a lot of stuff. And even if it's just a term, it's like you'd be searching for the internet. But if you don't have the right term, it's like having magic words. It's like, and that's probably the best part about a lot of the large language models is that if you're trying to ask it for a thing, it's going through, and even I feel like some of the calculations for some of the things have maybe gotten less great over. And I even say that about the Wolfram LLM. I'm not sure it's or the Chat GPT plugin. I don't know if it's been updated for a while. That's why I just go to the site and do it myself. But as far as asking about things, it will give you sometimes terms that you've never heard of. And you look into that term, it's like, oh my God, this has been right next to where I've been looking, but I literally needed that word. It's like speak friend and enter. I forget the Elvish word for friend, but as long as you have somebody that can speak Elvish, you might be able to enter. Now I got to drink some coffee and see what else has been going on and with our chat here. Let's see. Hmm? Oh, it's Griswold. What's going on, my dude? Haven't seen you for a while. Good to see you. Put out a now magnets. I still think. Do I have that clip still? I didn't upload it here. Where Sean Carroll is quoting the insane clown posse. And it gets to the point, magnets, how do they even flippin' work? They use different language than flippin', but the point is communicated. Uh now, see, that's the thing. What was it? There's like the tennis racket effect. Veritasium did a great video about there was some cosmonauts back in I think like the 80s or something, and they had like one of these like butterfly bolts, and it came off, and it's spinning, and then all of a sudden it did like a complete 180. And you're like, what? Oh, maybe that's something about angular momentum. It's kind of like if you flip a tennis racket, like it flips up, and then it does like a whole thing around based upon uh something about like the mass distribution and then where you're swinging it from. And then some folks are like, wait a second, magnets. We don't know how magnets work. What if this happens to the Earth? Now, I have no idea. I ain't a geologist. I ain't a cosmologist or anything. That thought terrifies me. I feel like would it happen slower? Because technically, doesn't the field change? That's why, like every X hundred or thousand of years, X number of 10,000 of years. I don't know the magnitude. Like the Earth's magnetic, the poles shift, so north becomes south and south becomes north. I mean, that happens to the sun, I think, like every 11 years or so. Um, as far as the full Earth flipping, probably a good thing it's not shaped like a tennis racket. Wait a second. I don't know, is that our argument for or against flat Earth type folks? Because some folks, it's personally, I don't know, maybe I'm just like a globalist or something like that. It looks pretty around to me. I don't know. I don't know. I haven't been to space. I've been in the sky and stuff before, and it kind of seems to curve a little bit. I don't know. I'm usually probably just looking for gremlins on the side of the plane, but that's me. Yes, yes. Planck volume has Planck density as Planck mass, or yeah, Planck volume is about 10 to the negative 104 meters. And you multiply a Planck mass, it's time. No, you divide that into the Planck mass, blah blah blah. Yeah, so it gives you like 10 to the 96. Uh it was memes talking about weird theories. So there's all types of weird theories. Um, and the thing is, a lot of time, even that paper that Dr. Hassenfelder was modern day engineering or something. They had listed this paper and it's supposed to unify things, and you read it like what they said. I'm like, all right, I've heard some of these claims before, and then you click on the paper and you go through. Like, all right, I'm not a professionally trained physicist, but I'm like, I'm seeing a lot of like errors. I'm like, I like some of the things were just left blank. I'm going through and I'm like, I'm doing some of the basic calculations. I'm like, these are just wrong. Like, just even just even going to, well, I'm like, well, maybe let me take the numbers from Cohen. I'm like, no, this is like the numbers don't match up, the powers don't match up. I'm like, are they just trolling us? I mean, like, were they trying? And but even within there, I saw something that didn't make sense, and I actually did the actual calculation. I think it actually helped me. I don't know if it was part of this, but it just had me look at a different relationship that I had not considered before. So it's, hey, you never know where a good idea may come from. Might it come from a crazy person? Yeah, statistically, probably at some point. All right. So let's see. We're coming up on hour at this time. So yeah. But long story is I've been meaning to do this for a while. I've completely been far too lazy, but yeah, I'm gonna start doing these on more probably like a Monday through Friday basis or something like that. Probably a little bit earlier in the day rather than after lunch. Uh Utah time. Probably post breakfast, maybe before lunch. So probably just so East Coast time, probably early to midish afternoon is where we're going to be shooting for like an hour or so. And there are some folks that I happen to know that are out there and happen to be there in the chat if they have a little bit of time and they would like to come up at some point and maybe have a little chit chat and maybe I could learn a few things. I mean, that would be pretty cool. But yeah, basically just dedicating like an hour during the day, do some science stuff. Listen, there's plenty of things you can talk about. People love to talk about all different things. Uh, I just created a account over on Blue Sky because there seemed to be some science folks that I follow over there, and I had totally thought I had created one. And then Jonathan Oppenheim, I'm just like, "Do you think it will last?" I created an account over there. He's like, "It seems to be slowly growing." He's like, "What's your?" I tried to recover my account. I'm like, I could have sworn I set something up. Apparently, I didn't because I sent to retrieve my password, and I don't know. Maybe the Blue Sky servers were just slow or something. So I just created a new account. I remember it like taking a couple of days before because they had to verify. This time it just let me create an account like extremely easily. Like I didn't have to have a waiting grace period or something. I think that's what happened. I think I started create it, I was approved, and then I just kind of lost interest in it. So I'm over at Blue Sky at Meme Destruction and whatever the Blue Sky tales are as well. But oh hey. Oh, thank you, Mr. Grant. It's well, it's fun stuff. And no, I mean I love science, and to be fair, it's like you have a lot of folks join different communities, fandoms, if you would, because generally like some things, and then some folks it's like oh, let's go off into here and there. And don't get me wrong, I'm okay. I like some woo woo as much as the next guy, but I don't know. Science has always been my personal safe space just because, like, let's have some ideas. And hey, every once in a while, you never know where a good idea can come from. And maybe it's kind of come from somebody that's in this chat right now or somebody watching temporally in the future. But got a lot of hope for humanity. And I think we're at the point now that this is full editorial here. I know this whole thing has been an editorial, I say conjecture ahead in the chat, or at least in the little doobly doo below. But my thing is I think this is how science should be, and that people have seen so much BS that they are open to new ideas that seem logical, that seem to make sense. And if you have some actual confirmed predictions, that doesn't hurt. I'm just saying we happen to have a couple more confirmed predictions in string theory, or at least experimental predictions. That was a little bit of jab. String theory is beautiful. I've talked to them grad students and like postdocs and stuff. They're like, oh, it's very beautiful. And I'm not here to take string theory away from anybody. It's like, I'm sure it's correct in whatever regime in which it's correct. Now, all I know, hey, Ruff, good to see you, my friend. Good to see you. We're not getting into hypothetical time stuff now. Maybe at some point we could get into some other things at one point or another. But for that, we're going on for an hour. Hey, thank you all for joining. Take care of yourselves, everybody. It's a crazy world out there, and other than that, I'll see you tomorrow. Peace out, everybody. There's the button. The button has